Sorry for that. So just so maybe in a couple of words, I would introduce what is ENGIE. It's actually a worldwide company with which has 4 main activities. One is related to the electricity production, so both from conventional thermal assets, so it's mainly gas, CCGT. And it's also based on renewable energies with wind, solar, geothermal, etc. Then ENGIE is also present on the production, transport, and distribution of natural gas. They are also present on new energies like green hydrogen and also biomethane. And finally, it's a provider of services, especially for cities and buildings. So ENGIE has also strong ambitions with regard to energy transition. It has 3 main targets. So the first one is to increase the share of the renewables in its electricity capacity by 2030 with a target of 58%. Then the objective is also to become a leader in the production of green hydrogen, so from water electrolysis. And finally, the target is to produce 5 terawatt-hours of biomethane by 2030. So within ENGIE, the R&D is organized in what we call thematic labs, which are spread over 2 R&D centers. I mean, there are 2 main centers. One is located in France, this is called Grigène, and one is located in Belgium, so La Bourralex, where I come from. And these 23 thematic labs are actually spread over the 2 R&D centers. They can be divided in 3 main categories. Some of them are related to the new energy, so basically on wind, on solar energy, but also on hydrogen, of course, and biomethane. Some of them are related to the new use of energy. And this, as an example, it's about the lighting, the green mobility, but also the CO2 as a resource lab, in which I'm part of it. And finally, there are some thematic labs which are more on the transversal activities. So as an example, some laboratories are specialized in materials with 3D printing capacities. One lab is also related to the water management, etc. So within the CO2 as a resource lab, actually our objective is to understand how the CCU, the CO2 capture and utilization, can be integrated in existing assets, and also to understand how it can create value. So we are looking at both the capture of the CO2, but also at the conversion, with as objective is to understand all the existing CCU technology, which are mature and less mature also. And the idea is actually to be able to identify the best technology for each application. Because as Claire mentioned, depending on the source of CO2, the specificities, but also on the project, the CO2 requirements, then the technology which will be suitable will not be the same. And with regard to the CCU technology, we also look at the flexibility of the CO2 capture technology. So actually, within ENGIE, since 2005, the strategy has been shifted. So first, we were considering CCS, and we were looking specifically at the CO2 capture from coal-fired power plant. But since a couple of years, I would say since 2017, then now we are looking more at CCU for different reasons. So basically, since 2005, we have been developing some expertise on carbon capture through the participation at different R&D projects, and also I mean, both internal, but also as part of collaborative project at European level. So that was the case of the project CESAR, Castor, Cato 2, Octavius also. And we have been also involved in the past in different pilot and demonstration projects. So the most, I would say, known demonstration project is the project ROAD, which was a partnership between ENGIE and Uniper. And with this project, the aim was actually to capture 1 million tons of CO2 for storage application. But unfortunately, this project was ended in 2017, mainly for economic reasons. So now we look at the CO2 capture because we considered it as the necessary and unavoidable step for the large-scale deployment of the CCU. So ENGIE is actually not a technology provider of carbon capture technology, but we can provide support for the design and the operation of a carbon capture project. And also we want to really understand the link of the capture with the utilization bricks. So today we are looking on the R&D activities on the CO2 capture bricks are on two aspects. So the first one, we look at the CO2 capture for ENGIE own assets. So this is typically the biogas upgrading plants, which produce a quite concentrated CO2 stream, which can be valorized. We look also at the CO2 capture from CCGT, which is quite challenging because of the intermittency of the operation of such asset, and also because of the low parcel pressure of CO2 in the gas stream. And then we look at the CO2 capture, the integration of the CO2 capture from different industrial sources as part of the complete CCU chain. So as I mentioned, so the idea for us is really to identify the best strategy to define the best CO2 capture technology from technical aspect, but also from economic perspective. And we really want to also address the flexibility of such technology with regard to the conversion of the CO2 to the Power-to-X technology, which require to have some flexible operation. So then, to support the selection of the carbon capture technology, we have developed in the past some analytical capabilities in order to have a deep characterization of the gas composition. So both in terms of organics, inorganics, so it's basically with a FTIR, which enables to determine at ppm level. We have developed some methodology to characterize the concentration of SO3 sulfuric acid aerosol in the gas stream. So that was mainly for absorption, amine absorption technology. And we have also developed a specific method to determine the particle size distribution in the gas stream, because with this information is very key if we want to predict if there is a risk of aerosol formation within an absorption column. More recently, we are looking specifically at the CO2 purity, because this is really at the core of the CCU chain. So we want to know what is the impact of the CO2 source and also of the CO2 capture technology on the CO2 purity. We want to know also how it can evolve with the time, because, for example, mainly for biological processes, which involve living organisms. In this case, we can observe some fluctuation in the CO2 purity which is produced. So this is very important to be determined based on the CO2 requirements, because depending on the use, if it's for storage, but if it's for the utilization, if it's for direct utilization, or if it's for the indirect use through conversion technologies, then the requirements will not be the same. And for some technologies, for some conversion technologies, even if the impurities are at ppm and even ppb level, in this case they can have some they can pose some issues for the technology. So why are we looking at CCU? Actually, this is linked with the ambition of ENGIE in terms of renewable energy and also with regard to the deployment of green gas, of hydrogen, because the major challenge for the deployment of renewable energy are actually the energy curtailment and also the transport and the storage of the energy. And in this context, the storage of energy as a molecule is considered as key, because it will enable the storage of the energy over a long period, if we compare, for example, to batteries. And also it will enable to transport over long distance energy. So from the area where the renewable energy is available, is abundantly available and also cheap, to the areas where the demand in energy is very high. And the second point is that the e-fuel are actually have a higher energy density in volumes compared to, for example, pure hydrogen. So over the last few years, there has been an increasing number of CCU pilot and demonstration projects within the group as part of different type of processes. So as an example, ENGIE is currently part of 2 consortiums which are developing some project on power-to-methanol. So ENGIE is more on the brick of green hydrogen. There are also some projects on power-to-methane, according to different type of processes, either by thermocatalytic hydrogenation, but also through bioconversion technologies. And at R&D level, I mean, we are looking at different type of process. So on the next slide here, voila. So at the R&D level, so the focus is really to evaluate all the CCU technologies which can exist at different TRL levels, so from the most mature to the less mature, and also to evaluate the integration of the CCU chain and the flexibility, as I mentioned before. So as an example, on the catalytic CO2 conversion, one project, it's a project C2 Fuel, which is coordinated by the ENGIE Lab Crégen, located in Paris. So in this case, the objective is to look at the CO2 conversion into dimethyl ether, and by using a different type of reactor, using a membrane reactor. Then on bioconversion, we are part of the project Biocon CO2, which was previously presented by Leita in the morning. And we also look, for example, at the concept of power to protein by some of my colleagues. Then at lower TRL, so we are looking at the electrochemical conversion. So we were part of the project ECO, which we are looking to the high temperature co-electrolysis. So I mean, this is the co-electrolysis of steam with CO2 at high temperature into syngas. And very recently, we are part of a project which is called Condor, which looked at the photoelectrochemical conversion. So the idea is to use the direct energy of the sun to convert CO2 into different byproducts. So in this case, in the project of Condor, the idea is to look at the conversion of CO2 into syngas, and then to look at the photothermochemical conversion into methanol and dimethyl ether. Okay, so to conclude, I summarized on this slide the different R&D topics we are considering within the thematic lab CO2 aerosol resource, both on the CO2 capture side, so from the concentrated point source, but also more as technology watch, we look at the CO2 capture from atmosphere. And in parallel, we look at the conversion of the CO2, so the energy storage as a molecule, first for the integration and then for the technology assessment of all CCU technologies. So that was my talk, so thank you.